We're interested in doing MCMC, that's constructing these biased random walks that if we simulate them, where we visit, we can see each site as being marginally a sample from a distribution. And Metropolis Hastings was this very generic way of constructing such a walk. You could use an arbitrary distribution Q to define your walk, except that just some of those steps you wouldn't take. You'd stay where you are for another time step. And the probability of actually accepting the move that Q took was this expression in the bottom left. So I said what you can do is you can go out and you can think of all sorts of different Qs. You could have generic ones, just like spherical perturbations on top of where you are. If you do have good approximations, you could try using those too. If your approximation turned out to be bad, doesn't matter, you'll just reject a lot when you try those updates, but the algorithm will still be valid. And so Hamiltonian Monte Carlo had this very clever Q where it was simulating a physical system, and I said that there's some technical worries when you do that sort of thing. And so I had this example where I asked you to see if you can spot the technical problem you've got to avoid. So in this example, I've got a real number between 0 and 10, and this is one of the updates I'm considering doing that I would combine with other updates in order to mix through the whole space. So this update can only bounce between any pair of points, but that's not the problem. You can just use other updates in the rest of your Markov chain. The problem is that this update is meant to leave the distribution invariant. And if my distribution were a uniform distribution, Metropolis Hastings is going to work with any target distribution. If this distribution were uniform, if I draw a sample, 0.9 of the time I'm going to be in the right-hand arm. This update will then take any of those points and put them over here. So under the target distribution, I should have mass of 0.1 in this region. Under this update, after one step, I'll have 0.9 of my mass over there. So this update upsets the invariant distribution. It's wrong. And yet it looks like it might be the right thing to do. So can anyone tell me where I've slipped up? OK. So the mistake was when I said, if I'm at 5.5, I'll always go to 0.5. So the probability of that is 1, and the other thing is 1. And I said, these are both 1s, and I'm going to cross them out. Right? So you've got to be very careful when you have real numbers, because the things that we write down as P's and Q's, they're not actually probabilities. They're probability densities, which are weird things. And if you have a deterministic proposal, then your probability density of that proposal is a delta function, which has an infinite peak in it. And you should be very worried if I ever write down maths that involves dividing infinity by infinity, and they're kind of different infinities, because one of these delta function peaks is kind of wider than the other one. So there is a version of Metropolis Hastings where you can do deterministic transformations, but when you do the deterministic transformation, you've got to multiply this thing by the Jacobian of the transformation. And this is something I don't have time to go in detail. But we should be correcting this factor by a factor of 9, and the moves from the right to the left, we should be rejecting them a lot of the time. So the problem is that this particular deterministic move stretches the space. I got a small region on the left, and I stretched that whole region out to a big region. The other transformation changed the volume the other way. You don't have to worry about this issue if the Jacobian of your transformation is 1. So if your deterministic moves didn't do the stretching, the volume, if you considered a volume in your space and where that volume goes under your deterministic transformation, if that volume stays the same, then this issue on this slide doesn't matter. It is OK to say this ratio of Q is 1, and you do just accept reject using the ratio of the target probabilities. So in Hamiltonian Monte Carlo that I was talking about, Hamiltonian dynamics, it's a thing in physics where we know that this maintains phase-space volume, and that thing is called Liouville's theorem in physics. So this particular physical system has been carefully chosen so that it avoids this technical issue, and that's why you see in the papers that it maintains phase-space volume, and they go on about it, and they talk about the fact that it's got unit Jacobian transformation. Okay. The thing is, we can't actually simulate Hamiltonian dynamics. That would involve solving a set of differential equations. We can't do exactly. We can just numerically simulate it sort of somewhat sloppily on computers that will introduce errors. And the way we simulate it might mean that we don't conserve energy. Sometimes when you run a physical simulation on a computer, you sort of lose energy somewhere. So I'm not going to go line by line through the algorithm, but a particular discrete approximation to Hamiltonian dynamics is popular, and it's these three equations I'm not going to go through, but I'm putting them up just so you can show that it's not very much. Like if you implement this as code, it's a few lines of code. David Mackay's book has a little octave demo of it. You'll find demos all over the place. And the reason people use this particular numerical way of solving differential equations as opposed to Runge-Kutta or some other system that you might have heard of is that these also maintain phase-space volume. The transformation that these equations has unit Jacobian. And that means that the acceptance probability is just the ratio of probabilities, or e to the difference in energies. So the sketch of the Hamiltonian Monte Carlo algorithm, just to remind you, is we've got a ball at some position in image space or state space. So if I'm sampling from this bivariate Gaussian, I start here. I kick the ball with some random velocity drawn from a Gaussian distribution. I then simulate, you can see these jagged lines. This is an approximate rough simulation of what a physical ball would do rolling around the system. And this motion is persistent. If you have a ball that will roll up and down the hills like this, and it will keep moving in some direction. Balls have momentum, they keep moving. And so when you simulate this algorithm, you have persistent motion for many steps. Unlike Metropolis, it would have this slow diffusive motion. And so on constrained high-dimensional systems, you don't necessarily have to know the directions that you can move in advance. Once it's found them, it can roll the ball persistently along those directions. So hybrid Monte Carlo was invented in physics. It's called hybrid Monte Carlo because there's this thing called the hybrid dynamical simulation method. Radford Neal has recommended renaming it Hamiltonian Monte Carlo, which a lot of people have picked up on. And this was what made Bayesian neural networks work. There's no way that you could simulate those many thousands of weights at all reasonably using Metropolis methods. Okay, Radford Neal last year released a book chapter on Hamiltonian dynamics. There's a lot of stuff in this chapter, so if you're interested in this area, I strongly recommend that. And it's also recently been, interest in Hamiltonian Monte Carlo has picked up again in the last few years. So here are 2 papers. There's probably another few that should be on this list. The slides are online. Okay, so I said the Monte Carlo, it looks as if the solution is just Metropolis Hastings. People often say that Gibbs sampling is a special case of Metropolis Hastings because you use, if you use the Gibbs sampling move as a proposal in Metropolis Hastings, then you see the acceptance rate is 1. And I don't actually like that argument because I don't like putting delta functions into the Metropolis Hastings rule unless I have to. One large area of MCMC methods are these auxiliary variable methods, because by coming up with different ways of representing our models, that's sort of where a lot of the fruitful research directions are in making these things work better. So I talked about Swenson-Wong, Hamiltonian Monte Carlo. If I had another half hour, I'd be talking about slice sampling. And embarrassingly, almost all of my MCMC research is literally looking at a problem, coming up with some way of rewriting it somehow, and then running Metropolis Hastings or slice sampling existing code on that, and that's all I've done in my research career. So it's a fruitful thing to do. Okay, so this is really the end of the the core MCMC part of the lecture. I'm going to go on to talking about density estimation, and there will be more MCMC technology brought in along the way, but are there any questions at this point about Monte Carlo in general? Okay, do stop me at any time. Okay, I was talking to I'll regret this later when I run out of time. I'm going to sneak in one little nugget of Monte Carlo knowledge, because I mentioned this to someone in the break and they were like, oh, I didn't know that. So often we're running Monte Carlo to gather simple statistics about a model that we're going to use in a training procedure or to report. So one of the statistics you might want is the marginal probability of some variable. So say I've got a Boltzmann machine and I'm interested in how often is this pixel turned on, and I might be using that in the gradient of my biases, for example. So I want to know what's the probability that xi is a 1. I could get that by simulating a whole bunch of random images using MCMC, looking at that pixel and just seeing how often it's on. So that's what the first equation says. I average under my samples the indicator function saying, is this pixel on? So if the pixel was on 7 times out of 10, I estimate the probability as being 0.7. Okay. And that's the obvious way of doing it, but it's not the best way of doing it. If you're doing Gibbs sampling, all along the way, you've also been computing how much this pixel wants to be on, the probability that this pixel is a 1 given the rest of the image, right? So in the first line, I was averaging real integers, zeros and ones. That's kind of a noisy thing to do to estimate a real number. But we've got all these real numbers that say how much the pixel wants to be on that we throw away if we just look at the hard choices that we actually made. And it turns out that if you average these conditional probabilities, that's also an unbiased estimator asymptotically of this marginal probability. So it's strange. I'm interested in pixel I, and the obvious thing to do is to look at only pixel I. The less obvious thing to do is to throw away pixel I and only look at the rest of the image in your sample, and that turns out to be a better thing to do. So this trick is an example of what's often called Raoul equalization, and I feel I should mention that. So that if you're doing MCMC, you have to pick your algorithm, you have to pick which representation you run your algorithm on. But even when you've done all that and you've got your samples, there might be different ways of using the samples, and some of those might be better than others. Okay, so I'm going to move on to the second talk. So we'll dive more into technical MCMC in a minute. But this talk is about doing probabilistic density estimation, and that could be for images. So you've seen a lot of talks about people who are modeling natural image patches, and don't worry, I'm not going to talk much about it because I'm not an expert. But I've been to a lot of talks where someone's wanted to give a nice tutorial introduction, and so they've said the following thing, which I don't really quite agree with, but it gives you some idea of what's going on. They said, I want to learn a probability distribution of images, so my model H says what a probability distribution of images is. What's a good model of images? Well, a good model of images would say, I assign high probability to things that look like natural scenes, and I would apply low probability to things that look like random junk. So I have some way of pulling out nice images. And that's sort of true to some extent, but there's one trivial thing that I just want to highlight, which is that just because something has low probability or high probability doesn't necessarily relate to how interesting it is. So if I've got this image of a sheet of concrete, then under most image models, this will have exceedingly higher probability than the image in the top right, because it's just so much easier to represent this because there's so little going on. And this image, where every single pixel is exactly the same gray intensity, and that any image compressor will tell you that the model of the density of this image is many orders of magnitude higher than the probability of this image. So if you do a good job of learning a probability of images, you've got to scatter your unit mass of probability very, very carefully in image space. You've got these really, really high but exceedingly narrow spikes around boring, smooth images. And then you've got these vast plateaus of incredibly low density across the vast number of interesting images. And if you do a good job of that, then you've probably learned some interesting hierarchical structure of the model. So I think, although it's a hard game to play, I think it's worth playing. This fact that the probability densities vary by many orders of magnitude is a complete pain for Monte Carlo methods. So if you've got a metropolis method which is trying to move between an image like this and an image like this ratio of probabilities is just incredibly extreme. And if you try to move from this image, which is totally boring, to this interesting image, it'll just go, well, this image is much worse. It's got much lower probability. I'm not moving there. And so you need to have very good proposal mechanisms, or you need to represent your image space very carefully. Okay, but I think this is worth doing. It's not everyone wants to learn a hierarchical probabilistic model of images. It might not be necessary for the task they're doing, but I just think it's scientifically interesting. One place where I think it's really worth having a decent probabilistic model of images is if you're thinking probabilistically and you can say a lot about your system. So there's a lot of image reconstruction problems where you have an observation model, you have a downsampled image, a noisy image, a blurred image, whatever it is, some corrupted image, Y, where you've got a good model of what that corruption process is. And if you're in that situation and you've managed to fit a really good model P of X of images, then Bayes' rule tells you what to do. You just say, well, I know what my posterior under the underlying image is, and now I can simulate from that. If you maximize that distribution, or you use some optimization task, you may well oversmooth the image because the high peak of highest density is always something that's really smooth, but there might not be much mass there, and so you want to do the full probabilistic thing and really understand this distribution. This is pretty ideal. No one actually does this at the moment. Most image reconstruction is all MAP estimation, but I don't think it should be. Zoran and Weiss last year had a really nice paper where they show for a variety of reconstruction tasks that it is actually the case that if you go in and you build a better probabilistic model of images, then that's strongly correlated with performance on the tasks. And by building a better model of images, it directly translates into doing better in the task, and they get state-of-the-art performance on various tasks. And Lucas Thijs, who's also here somewhere, is people in there at the back. People in his lab have been having a similar experience, and they have very sophisticated models of images that I recommend you look at. I'll plug his work later as well. And that's not always the experience for feature learning and deep learning in general. So I'm going to be telling you about how to work out these probabilities and how to evaluate probabilistic models. And it could well be the case that you fit a better model, it gives better densities, you extract its features and you throw them into an SVM and your classification performance goes down. And that's happened to me, and I'm sure it's happened to other people here. And I was chatting with Iain Weiss about this, and he said, well, who said that you were supposed to extract these filters and throw them into an SVM in the first place? So here, when you've got an observation model and a model of underlying images, it's clear how to proceed. Like, the probability calculus tells you what to do. And so it's really worth evaluating the models and working harder. And I think what concerns me a bit about a lot of the feature learning at the moment is there aren't clear inductive principles that tell us what we should be doing. And so it's not clear necessarily how to make methods better. So I would personally like to see more like principal probabilistic machinery being imported, although it's sort of the low-hanging fruit of engineering performance. It's not always the first thing to do. Okay, so that's my bit of rant about why I like probabilities again. So back to the Monte Carlo. So if we are playing this game of trying to build a better probabilistic model because we think it's interesting and we think ultimately it might help, what we need to do is be able to honestly compare these models. And so for different models, we need to be able to say, what's the probability this model assigns to the test image compared to this other model? And so I'm going to describe a bit of work that I've done with Russ and others on this problem. And if I have time, yeah, I will have time, I will then say how to sidestep this whole issue and sidestep Monte Carlo, because who wants to do Monte Carlo? It's hard. And I'll describe some work with Hugo La Rochelle where we do density estimation without Monte Carlo and without having to approximate things. Okay, so this is how I see a restricted Boltzmann machine. It's this big mass of weights, and there's an equation, and it's a bit of a hairy beast. But ultimately, given some parameters, it assigns probabilities to images, and that probability is e to the minus 3 energy. It's just some function that we know how to evaluate. Except in front of it, there's, as we know, this normalizing constant that we can't evaluate. So let's say I fitted a Boltzmann machine to images, binary images, say. I want to know, has this actually worked well? I've been told by Jeff Hinton that restricted Boltzmann machines are the way to go for binary m-ness digits, but is it actually better than, say, Chow Lu or a mixture of multivariate Bernoullis or any baseline model I could think of? Question, sorry. Yeah, okay. So Boltzmann machine has 2 layers, visibles and hiddens, and I've said that I'm only interested in the probability of the visibles, and there's this sum over the hiddens that I have to do. And I've said that this sum over the hiddens is tractable, and the question is, like, why is that tractable? It's a massive sum over a high-dimensional space. And usually it isn't, and I'll return to this issue. But for the special case of an RBM, because none of the hiddens are connected directly to each other, and because of this graph structure, it's possible to do this sum. And it's this equation that's the thing that looks like a product of experts, so I refer you to that paper. So yes, we'll return to what happens when you can't sum out H in 10, 15 minutes. Okay, so if we assume that I'm right, and I do have a blob of code that can compute this, I can't say what the actual probability of a test image is unless I know this number, and that means I can't compare this model to any other baseline. So it's only one number, it's one scalar value. Like, how hard can it be to approximate it? I mean, we might not be able to compute it exactly, but who cares as long as we can estimate it. Right. So let's have a look at what we're doing. We've got this probability over images, which is some green function that we can compute. And to normalize it, we need to divide by the white area underneath the green curve. So what we're doing is working out that area. And z, it's just an integral, so we could imagine trying to approximate that integral with Monte Carlo. If you write down the obvious importance sampling estimate of z, then the obvious thing to do is to draw from a uniform distribution or a simple base distribution, and then look at those samples and process them somehow. So again, your homework is to work out how to normalize, work out why that expression for computing normalizing constants is correct. Okay, so what do uniform samples from image patches look like? They look like this. And hopefully you'll believe me when I say you'll be waiting an incredibly long time before one of these patches actually looks like something like this. So if you draw uniform samples, they're all with exceedingly high probability and this vast basin of things that don't look like the data. Okay, so z, the normalizing constant, is dominated by this area around where things look like plausible images in our training set. And all these samples, when we're doing dumb importance sampling, are not in that important region. So there's no way these samples can actually tell us anything about how high this region is or how wide it is. There's just no information in them about that. So, I mean, we could try and mathematically show this and compute variances, but it's just clear that those samples aren't useful for evaluating our model. Okay, so those samples are useless. Maybe we could use MCMC, Gibbs sampling, or Metropolis, whatever, to draw samples from our model. Maybe these samples, these are fantasy digits drawn from some model, they could tell us what the area of this region is. So what can these samples tell us? So if we've got these blue dashes, which are our samples of digits, then we can evaluate how high this curve is. That's e to the minus free energy, the thing that I'm saying that we can compute for RBMs. But what we're interested in is this area under the curve. So we've got this hyper area in image space, and we've got a height, which is the unnormalized probability. And we can evaluate the height, but we're not actually in 1D. This is a hyper area in image space, and that's computationally exceedingly hard to compute from samples. So theoretical computer science results about computing volumes from samples, and it's just not something that you want to try and do. So if you've got a bunch of samples from your model, you can look at them and say, oh, wow, aren't they pretty? But they don't actually tell you the partition function. So drawing from a base distribution doesn't help. Drawing from the model doesn't help. Maybe we could try doing something in between. So there's this idea of annealing or tempering, which interpolates between a base distribution, which on this slide is pi. So pi could be uniform, or here, these are samples from pi. It's actually using the visible biases of the model with all of weights turned off. And interpolating between some base distribution that's tractable and a distribution p star that we're actually interested in. And beta here is an inverse temperature, more physics, but if beta is 1, then the base distribution turns off and we're left with the model we're interested in. So here's beta equals 1 on the right. And if beta equals 0, we turn off the distribution entirely. We're effectively multiplying the weights of the Boltzmann machine by 0, and we degrade to the base distribution. And for betas in between, we slowly make the digits appear when we draw samples. So for a real valued density, this is the sort of sequence of different distributions we get. Sharp spikes slowly disappear as you send beta down towards 0. So you may well have heard of simulated annealing, which is a science paper in the 80s. Simulated annealing is where you run the Metropolis algorithm starting at beta equals 0, and then you slowly increase beta towards 1. So it's you slowly increase beta towards infinity. It's a heuristic for slowly turning on a cost function so that you end up in a sharp spike and hopefully avoid local optima along the way. So I'm not talking about that. I'm not doing optimization. I'm wanting to use this to help me do sampling and help me understand the probabilistic model. Okay, so I'm going to do something completely unreasonable. I just want to say up front how unreasonable this sounds. What I want to do is I want to use this sequence of temperatures and do something that looks like simulated annealing, but import it into importance sampling so that I can compute normalizing constants. So rather than showing the maths on the next slide, I'll tell you what I'm going to do. I'm going to start off by sampling an image from my base distribution, which I can do because the base distribution is tractable. I'm then going to slowly increase the temperature and run a Markov chain the whole time I do that. So I'm going to run one step of my Markov chain with beta equals 0.01. I'll then set beta equal to 0.02 and run another step of a Markov chain, and slowly end up at one of these digits. Okay, now that whole sequence of operations, maybe I went through 1,000 temperatures, defines a joint distribution over 1,000 images. Okay, so what I'm going to do is call that joint distribution over 1,000 images big Q. So the first node in this graphical model for Q is draw from my base distribution, run one step of MCMC with operator TK that uses a particular beta, draw a whole load of images, and this whole stack of images I'm going to call one random variable drawn from Q. Okay. So I've written down an equation for what the joint distribution of Q is. And now I'm going to compare that to a distribution which starts at the other end. So P is an intractable distribution because it draws from my model. This is something I can't do, but I can write down. So P starts with a perfect sample from the distribution and then heats up and draws a series of images which get hotter and hotter until I have something that looks like random noise. Okay. So I've got these two enormous distributions. I started off with something that was like 700 dimensional, and now I've got something which is 700,000 dimensional, a whole stack of images. And now I'm going to do dumb, simple importance sampling on these two distributions. And that will give me an estimate of this normalizing constant that I don't know in big P, which is the normalizing constant of the model, the one I'm interested in. Pictorially, I start off with a hot image, I cool it down, and that's Q. I compare it to the reverse process, that's P. I find the ratio of those two things. I do this whole procedure multiple times, and that is an estimate of Z. So I told you that importance sampling doesn't work in high dimensions, so you can't apply it to Boltzmann machines because, MNIST digits have 700 dimensions. And now I'm telling you that I'm going to solve this problem by doing importance sampling in 700,000 dimensions instead. And the reason, well, it's not clear that this will work, but the reason it works is that when you change the temperatures very, very slowly, running these Markov chains in opposite orders are very similar things to do. So these two big joint distributions are actually very close. And it turns out, if you read the paper, it can show you this more formally, that the variance of this estimator can actually be quite controlled. So if we do this for a Boltzmann machine that only has 20 hidden units so that we can, by brute force, work out what log Z is, this is a sort of the behavior of the algorithm. For early times, you underestimate with very high probability, and you get very large error bars, you get weights that are all over the place. But if you run this thing for literally hours, then you can estimate log Z of this very high dimensional distribution. So working out this one number is, I think, you can sometimes come up with reasonable estimates, but it's not a cheap thing to do, even though it's just one number, and we have some methods to do it. Okay, so this isn't the only way of finding Z, but you'll see in the machine learning literature there's an enormous number of papers on computing normalizing constants. There's many Monte Carlo methods, and there's also many deterministic methods. So Russ and I did try a bunch of these, and there are other Monte Carlo methods that also work. There's a bunch that don't work, but most of the deterministic methods completely fail on this problem. Again, it's this problem of comparing to the wrong distributions. If you read a lot of NIPS papers on computing normalizing constants, they have little experiments on tiny icing grids, and they're just nothing like the distributions that you get when you fit to data. Okay, so In a minute, I'll say what we do with this, but I just want to point out that there are other ways of using temperatures. So there's this thing called parallel tempering, where you also use temperatures, but you do them in a different way. So now our Markov chain is over a stack of variables, which are, one of them is drawn from the distribution you care about, and then the rest are drawn from distributions with different betas. So this whole column is our new variable. And then, so it's an auxiliary variable method. We run a Markov chain on that whole column, even though we're only interested in the first row. And what parallel tempering does is it tries to swap states between the rows. So the bottom row, which is running at a very hot temperature, the Markov chain mixes really quickly. And the hope is that some of that information, it may be found different modes, can eventually diffuse up to the top row by doing swaps. It's not clear whether this will work for your problem. It's not clear how to pick the temperatures. I have more things I could say about that, but I'll put my hands up and say that making these things work is a bit of a dark art. There's at least like 5 different tempering algorithms for MCMC. There's another one that's good is temper transitions, where it's a proposal mechanism in a Markov chain. So again, I won't go into the details. Just see this as a big metropolis move. You start somewhere, you heat up your images, you cool down again, you get somewhere else, maybe in a different mode, and then that whole procedure was just an elaborate proposal which you accept and reject. The reason I'm mentioning both of these is to point out that you can do tempering within MCMC. The algorithm I showed you here is importance sampling. And what worries me about importance sampling is that it's possible to have very high variance importance weights and very bad things happen. If you do some fancy tempering heuristic within MCMC and you heat it and cool too aggressively, then all that will happen is your move will get rejected, and hopefully the other Markov chain operators that you're using, that you should be using, will sort you out. If all you're doing is importance sampling with some Q, then you could be in trouble. So I'm personally massively in favor of embedding these fancy schemes within MCMC. And recently there's work on particle MCMC where people doing particle filtering also come to this conclusion that embedding particle filters within MCMC is a good idea. All right, so don't really have time to get into the nitty-gritty of annealing and tempering. I'm just giving you this flavor that in order to compute Z, it's not a simple task. There's no obvious thing that you can do to samples from any one distribution that tell you Z, because it involves working out hypervolumes, which are just computationally hard things to compute. So all of the methods that will work on large-scale Boltzmann machines involve looking at sequences of different distributions. And they're not always defined with temperatures, but it's an obvious choice. The reward for these methods is that they do have these annealing heuristics in them. So if you're worried about getting trapped in little modes of your distribution and not your Markov chain not exploring the whole space quickly, then these tempering methods can solve that problem for you as well. So even if you're not interested in the normalizing constant, you might want to zoom around your space faster by heating it up and then cooling it down again. Okay, so what can we do with estimates of the normalizing constant? And I believe that Russ has already shown you this demo, so this will partly test your memory and partly make you see where it fits in. So he got 60,000 binarized MNIST digits, and he fitted an RBM to them, and then you can ask the question, which is better? Is it the RBM or this baseline model that we can fit with EM, this mixture model, and we can compare samples and we can compare log probability? Did you see this figure before? No, okay. So one of these panels shows 16 samples from a Boltzmann machine, and one of the panels shows 16 samples from a mixture of multivariate Bernoullis, and they were both fitted to the same 50,000 digits. The mixture of Bernoullis model, per test digit, it has probability minus 143 nats. So in other words, you can compress each of the digits with that model into 143 nats of storage space. The restricted Boltzmann machine is hugely, hugely better in terms of compression. It can compress into only 106 nats. Any model comparison measure that you'll find in the statistics literature will say that the RBM model is obviously the better model than the mixture of Bernoullis. It doesn't matter how you penalize these likelihoods. the Boltzmann machine has much better probability. So the question is, which way round are these fantasies? I know someone will know. So what's the one on the left? Yeah, so the one on the left is the model that's hugely better. There's fantasies from digits, and you can see these beautiful digits, right, as opposed to the ones here. So we can tell this is a mixture model because a mixture model says the way I'm explaining images is I've got a template image, so I've got my prototypical 4, and then I add noise to it, or I pick a prototypical 5 and I add noise to it. And you just can't tile a whole space of images with enough prototypes. So the only way you can explain the data is by adding lots of noise, which is why these things look like incredibly noisy prototypes. The RBM doesn't have that constraint, but it also means that it doesn't have to be close to something sensible. And what's happened here is that 99% of the probability mass of the RBM is on this spike near the all-zero vector. If I remember correctly, I think 7% of its probability mass is exactly on the origin, which is an awful lot of probability mass to put on a single image. And then the rest of its sort of 1% of probability mass is spread really neatly over the manifold of digits. So if you sample from this model, 99% of the time you get something that looks almost black. But when you ask how much that's penalized in terms of log probabilities, well, the log of 0.01 isn't that an extreme a number. So it doesn't actually pay very much in coding costs to say, by the way, you're not in this massive mode, you're in this other mode over here. And so, log probability just is only one measure of how good a model is, and looking at the samples, we get a different measure. What is, by the way, this failure mode is a result of using CD1, contrastive divergence. During the training, the learning algorithm just couldn't see this massive mode near the origin, so it never crushed it down. So if you don't use CD1, if you use CD25, and you fit an RBM, then you get much more reasonable looking samples. They don't look perfect, but they do look quite similar to the training set examples. And you do get some win for this. So the test log probability is now 20 nats better. Our model comparison measure does fortunately tell us that this better fitting model is by far the best model of any of the ones that we fitted. Okay, so back to the question I had earlier. We've now worked out how to compare restricted Boltzmann machines to other baselines. The problem is that people are very creative and come up with all sorts of models. So there are these deep belief net things. You could decide to link up the hidden units with undirected connections. Any directed model with latent variables will have explaining away phenomena. So unless the model is very constrained to be something like a mixture model, you can't sum out any latent variables. So we're interested in latent variable models where the probability of an image involves a sum over the hiddens, and usually this sum is intractable. In fact, for RBMs and mixture models are basically the only case where this sum is tractable. And so what are we going to do about it? So one answer is that we could run annealed importance sampling. So before we ran annealed importance sampling to estimate this one number z, and it took like 5 hours, right? But that was okay. I'm prepared to do something for 5 hours to evaluate a model carefully. This sum, though, I'm going to have to do for every single test case that I want to evaluate the probability of. So I don't want to run a 5-hour procedure for every new test image I see, especially if I've got a test set of size 10,000. Right? So that's unfortunate. I've put a Necker cube in the corner of the slide to remind me to say something. There's something fortunate about these models, which is they're often have pretty simple posterior distributions over hiddens. So some images are very ambiguous. The Necker cube is famously ambiguous because when you see this visual scene, you're not sure how to interpret it, and you bounce between 2 or 3 different interpretations. But actually, most images aren't like that at all. We know damn well what's going on. And so we get very peaked distributions over hidden variables. So these distributions are fairly simple, and we should be able to exploit that to compute this sum, because the sum shouldn't be too complicated. I'll sketch roughly how we do that. Here is Bayes' rule. We've got the posterior distribution over hiddens given an image, which I'm saying is simple, and this is Bayes' rule for that. And if I evaluate Bayes' rule at any particular special state I like, so maybe I could find the most probable hiddens that I could find by just greedy coordinate ascent or something, I can evaluate Bayes' rule and rearrange it, and that gives me an expression for the probability of a visible vector. So if I know this joint probability usually, at least if I've gone away and estimated Z, I know this joint probability. What I don't know is the posterior probability of this special state given an image. So I've got an image, I don't know what the hidden state is going to be, so I've got a distribution. This posterior distribution is unnormalized, so I can't evaluate this probability here. But this idea, which is due to Chib, is I could go away and estimate this one quantity for the particular test image I'm interested in, and then I'd have an estimate of the probability of that image. So now what I have to do is, for my test image, I use Monte Carlo to explore the posterior over hiddens, and I look at how probable that hidden vector looks like. Okay. So one thing I could do is I could simulate from the posterior distribution over hiddens and say, how often do I visit that hidden vector? And that would be an estimate of that probability. As you can imagine, in a high-dimensional space, I might not visit any one particular point that often. I can also do a Raoul equalization thing. I could just say, well, how much did the chain want to walk to that hidden state at each iteration? And so there's fancier estimators we can apply to our sampler, and that's roughly what we did. So this one thing, I've got this peak distribution, how probable is one state, is a lot easier than trying to sum over the whole space of images, which is what's involved when you're computing Z. Okay, so you can also do variational approaches, they don't work so well. Here's an example result of what happens when you fit a deep belief network to natural scenes. You get some variational lower bound on the performance. I'm not a big fan of variational methods because they're often way off. If you do if you do AIS for every test image, so you've got a big cluster and you're prepared to burn computer time to write a paper, then the red line shows what test performance we think this model has, and the blue is our fancy estimator that I encourage you to go and read about if you ever need to evaluate this sort of model. So along the x-axis is how many sweeps of Gibbs sampling we had to do in order to estimate what's going on. So only 20 or 40 sweeps of Gibbs sampling are required in order to work out the probability of a test image and agree with the gold standard annealed importance sampling. So I'm interested in the Monte Carlo methods, and I was kind of excited to see this working quickly. But something else that we learned from this is that these models were terrible. So we're fitting Gaussian Boltzmann machines to natural image patches, and these numbers on the y-axis are all disastrously bad. So if we plotted where the performance on a test set of a mixture of Gaussians was, it's way, way up to the ceiling and beyond. It's like much better. Independent components analysis work better. So we've got these very sophisticated models that are meant to work well, and yet their probabilities that they're assigning to images weren't so hot. So this sort of exercise of testing these models taught me a few things. But one was that I went to Toronto a bit of a skeptic about Boltzmann machines and deep learning, but if I wanted to have a generic density estimator of binary data, RBMs are, except the thing I'm about to tell you about, by far the best thing I'd seen, and they outperformed everything else by a long way. On MNIST, which is, as we all know, relatively simple data set, it didn't actually help well to go deep. So you need more sophisticated, interesting data sets if you want to test bed for deep learning. And I think that this sort of really motivated me to get excited about more interesting models of natural image patches that capture covariance and the sorts of things that have come out in the few years since we did these experiments. As an aside, the topic model literature, which is a huge part of machine learning, has many statements about what the perplexities of their models are, or what are the probabilities that their topic models assign to test documents. And almost every single paper, at least before a couple of years ago, those statements they're using Monte Carlo methods that just can't work. They're using important samplers that will have massive variance and will massively underestimate their numbers. If you are doing anything related to topic models, you should look for a paper where I'm on the author list somewhere that tells you how to actually estimate these probabilities. That's the end of all of the Monte Carlo technology that you're going to get from me for today. as part of this sort of discussion of like how to evaluate these models and how to get good density estimators, Hugo La Rochelle has developed this great thing called NADE, and I want to just spend the last 5-10 minutes or so before questions telling you about how that works, because it also relates to how to evaluate these models. It sort of neatly brought together the Monte Carlo and neural network work for me. So the one technical thing that we're using in this work is the chain rule of probability. The fact that if you've got a joint probability, then any probability distribution P can be factored into first output the first pixel, and once you've output the first pixel, clamp it and output the second pixel, then clamp that. Given the first 2 pixels, output the third pixel, and so on. Okay, so this is an identity. You can write it down for any probability distribution, and it factors this high-dimensional thing into a series of 1D distributions, which might be easier to deal with. The reason that, of course, I haven't solved any problems yet is, although this distribution is 1D, it's conditioned on a high-dimensional vector. So if I want to represent arbitrary distributions, I've got an enormous table here of possible conditional distributions. Okay, but given this decomposition, maybe we could approximate or simplify these massive tables, represent them compactly or parametrically, and this might be a sensible way of representing probabilities. We're not by any means the first people to notice this obvious fact. So this is what we're going to do. We're going to try and our target for learning is going to be, for any set of pixels, we're going to want to be able to predict the next pixel. And if we can solve this one task of predicting 1 pixel at a time, then we can plug that into this equation and get a density. Okay. So one way that you could come up with these conditional probabilities would be to say, these look like logistic regression problems. I would need a probability of a binary variable given some features. So for every such question, I could just fit logistic regression. I could consider every possible window of pixels where I'm going to have to make a prediction and fit a logistic regression classifier to spit out the next pixel. And that thing has a name. It's called the fully visible sigmoid belief net. And this thing, it's nice because all of the logistic regression problems are convex, so it has a unique solution, although you might want to regularize it or early stop, and then it's not clear what to do. But it's fairly well defined, and it actually gives you pretty competitive densities on a lot of problems. So if you want a generic density estimator, this is a reasonable choice. It would often be better than a mixture model or Charlie. But it doesn't work as well as the probabilities that we were getting for RBMs. And is that because we're not computing Z properly, or is it because we can do better than this model? So to answer that question, we thought, well, another way that we can get this conditional probability of 1 pixel given all the ones we've predicted so far is that we could try and do approximate inference in the RBM and answer this question. So if I run Markov chain Monte Carlo on an RBM for an incredibly long time with some of the pixels clamped, I can then come up with a Rao-Blackwell estimate of what this probability is and use that as my prediction machine. Okay. So if computer time isn't an issue, I can get a trained RBM. I can then make a prediction machine out of it that will predict new images 1 pixel at a time by doing lots of MCMC to make each of those predictions. And that complicated stack of prediction machinery does produce a predictive distribution that sums to 1. It's not possible for me to cheat there. And it's also a way of estimating Z, because if I have a probability assigned to an image using this procedure of sampling from the conditionals, and I have it with AIS, I can compare those numbers and see if they agree. So this is something that I did do. I ran MCMC on RBMs for weeks, and eventually I got numbers very comparable with the AIS results. So I do actually believe that we can compute Z for RBMs if we're careful about it. Hugo's idea was that instead of MCMC, which is expensive and horrible, who wants to do Monte Carlo, we could do mean field estimation in the RBM to approximate these conditionals instead. So we could get a trained RBM with some weights, and we could use those to activate the hidden. So instead of sampling the hiddens, we get a deterministic activation of the hiddens. We use that deterministic activation of the hiddens to then activate the visibles and predict what the next pixel should be when we've put in some of the inputs so far. And so the ideas were we could approximate RBMs with MCMC or mean field. MCMC is going to win, right? We're going to get better predictions if we use MCMC than mean field. But that's if we've clamped the RBM and we've fixed what we're doing. An idea is that this thing with mean field just defines a bunch of conditional distributions, and it's got a whole bunch of free parameters, W and H, and you could actually give it two different weight vectors. You could say that we'll use a different weight vector at this stage of the prediction than this one. And that's something you could fit directly. So rather than fitting an RBM to data, you could just say, this is an interesting looking piece of prediction machinery. It relates to RBMs. It might be a sensible thing to do, but we can fit these parameters to actually do well at the task that we're interested in, which is density estimation. So NADE is a bit of a crazy name, but the neural autoregressive distribution estimator says, we've got this prediction machinery which is derived from doing approximate inference in an RBM, but we're going to fit its parameters so that it does well at predicting pixels one at a time. And the particular parameter tying that goes into here means that it seems less prone to overfitting than a bunch of other neural network solutions to this problem. And the computational cost is reasonably under control relating to the input dimensionality of the problem and the number of hidden units. So a lot of fancy methods involving putting trees on your data and thing might be d-squared. So we've now got a means to have an estimator that's linear in the dimensionality of our problem, and we can fit this thing with gradient descent. So we have the standard table in the paper with a bold line saying we do better than everything else. And this thing generates reasonable samples, and it gets performance comparable to the RBMs. But the difference here is the whole thing is tractable. We can actually evaluate our cost function. We can do plain gradient descent on it. We don't have to do any MCMC. And when we report our test performance, we know that our test performance actually was minus 88.86 nats, as opposed to the RBMs, where we're saying, well, it's probably minus 86.34 nats, but if we messed up with our annealed importance sampling, it could be arbitrarily worse than that, which is not a very solid statement. Okay, so I'll stop there and take questions. I've talked about why I like learning probabilities, the Monte Carlo methods that go with it, and I've just told you that autoregressive models where you go one pixel at a time are a pretty compelling way to go about it. And Lucas Thijs, who's sitting at the back, his work with Matthias Becker and his group, they have much more sophisticated autoregressive models for real data. I suggest you check those out as well. Thanks very much.